Welcome to the e-lecture session for diploma students. In today's session, we are going to discuss about the various connections involved in primary and secondary of transformers. The first one being star delta connection. In the previous sessions, we have covered star star connection, and we have discussed various advantages and demerits of that connection, and now we are moving on to the next one, which is star delta connection. In this type of connection, the primary is connected in star while the secondary is connected in delta as shown in the figure 4.5. So, this is the primary side, star connected primary side, and delta connected secondary side. The same type of connection can be represented in another way as shown in figure 4.7. Here it is just remodified, the star connected primary is just remodified as shown in the figure 4.7. Here one end of all the phases A, B and C are interconnected, whereas the other ends are left free like this. So, this point is a neutral point where the point is taken from where you interconnect all the ends of the phases. On the other hand, in the secondary you have a delta connection, that is the second end, that is the second end of each phase is connected to the first end of the other phase. So, you can see here the second end of A phase is being connected to the first end of B. Similarly, second end of B is connected to first end of C. Similarly, second end of C is connected to the first end of A, thereby forming a delta connected network. This type of connection is commonly employed at the substation end of the transmission line. The main use of this connection is to step down the voltage. The neutral available on the primary side is grounded. It can be seen that there is a phase difference of 30 degrees between the primary and the secondary line voltages. This connection suffers no problems due to the unbalanced load, as the secondaries are connected in delta. These type of transformers are commonly employed at the receiving end, that is at the distribution end. So, here are the few advantages of star delta connection. Here the primary side is star connected, hence fewer number of turns are required. This makes the connection economical for large high voltage step down power transformers. Number 2, the neutral available on the primary can be earthed to avoid distortion. Large unbalanced loads can be handled satisfactorily. Then disadvantages: in this type of connection, the secondary voltage is not in phase with the primary. Hence, it is not possible to operate this connection in parallel with star star or delta delta connected transformer. Then we will move on to the third third configuration, that is delta star connection. In this type of connection, the primary is connected in delta fashion while the secondary is connected in star fashion as shown in the figure 4.8. Here you can see just the reverse of the previous connection. Here the primary side is delta connected and the secondary side is star connected. So, this is another way of representing the same type of connection. The main use of this connection is to step up the voltage, that is at the beginning of high tension transmission system. It can be noted that there is a phase shift of 30 degrees between the primary line voltage and the secondary line voltage. As the secondary side is star connected, the implementation of 3-phase 4-wire system is possible. So, here are the few advantages. Due to the delta connection present in the primary side, the cross sectional area required is less. On secondary side, neutral is available, due to which it can be used for a 3-phase 4-wire supply system. There is no distortion due to the third harmonic components. The windings connected on star makes it economical due to saving in cost of insulation. Large unbalanced loads can be handled without any difficulty. So, here are the few disadvantages. Due to the phase shift between the primary and the secondary voltages, it is not possible to operate this connection in parallel with a star star or delta delta connected transformer. And the fourth configuration is delta delta. So, here the primary is delta connected, the secondary is also delta connected. In this type of connection, both the 3-phase primary and the secondary windings are connected in delta as shown in the figure 4.11. The another way of representing this connection is shown here in 4.13. This connection proves to be economical for low voltage transformers as it increases the number of turns per phase. So, here are the few advantages. In order to get secondary voltage as a sinusoidal one, the magnetizing current of transformer must contain a third harmonic component. The delta connection provides a closed path for circulation of third harmonic component of current. The flux remains sinusoidal, which results in sinusoidal voltages. Even if the load is unbalanced, the 3-phase voltages remain constant, thus it allows unbalanced loading also. The important advantage with this type of connection is that if there is a bank of single phase transformers connected in delta delta, and if one of the transformers is disabled, then the supply can be continued with the remaining 2 transformers, of course with reduced efficiency. There is no distortion in the secondary voltages. Due to the delta connection, the phase voltage remains same as the line voltage, hence winding has more number of turns, but the phase current is 1 by root 3 times the line current, hence the cross section of the winding is very less. This makes the connection economical for low voltage transformers. So, disadvantages: due to the absence of neutral point, it is not suitable for a 3-phase 4-wire system. Scott connection or TT connection. So, 3-phase to 2-phase conversion and vice versa is needed under the following circumstances. Number 1, to supply power to the 2-phase electric furnaces, to interlink 3-phase system and 2-phase systems, to supply power to 2-phase apparatus from a 3-phase source, or finally to supply power to 3-phase apparatus from a 2-phase source. The common type of connection is to achieve the above conversion is generally called as Scott connection, and this is represented by this schematic diagram. So, this is a connection by which a 3-phase to 3-phase transformation is accomplished with the help of 2 transformers as shown in figure 4.14. Since it was first proposed by Charles F. Scott, it is frequently referred to as Scott connection. This connection can also be used for 3-phase to 2-phase transformation. One of the transformers has center taps both on the primary and the secondary windings, figure 4.14, and is known as the main transformer. It forms the horizontal member of the connection. The other transformer has a 0.866 tap and is known as a teaser transformer. One end of both the primary and the secondary of teaser transformer are joined to the center taps on both primary and secondary of the main transformer respectively, as shown in figure 4.15a. The other end A of the teaser primary and the 2 ends B and C of the main transformer primary are connected to the 3-phase supply. Here the 3-phase supply voltage is assumed to be 100 volts and a transformation ratio of unity. For understanding as to how 3-phase transformation results from this arrangement, it is desirable to think of the primary and secondary vector voltages as forming geometrical T, from which this connection gets its name. So, in the primary voltage T of figure 4.15, EDC and EDB are each 50 volts and differ in phase by 180 degrees, which means that EDC and EDB are out of phase with each other with an angle 180 degrees in between them, because both the coils DB and DC are on the same magnetic circuit and are connected in phase opposition. Each side of the equilateral triangle represents 100 volts. The voltage EDA being the altitude of the equilateral triangle, which is equal to 86.6 volts and lags behind the voltage across the mains by 90 degrees. The same relation holds good in the secondary winding, so that ABC is a symmetrical 3-phase system. With reference to the secondary voltage triangle of figure 4.15, it should be noted that for a load of unity power factor, the current IDB lags behind the voltage EDB by 30 degrees and IDC leads EDC by 30 degrees. Here you can see this is IDB, which is lagging behind voltage by 30 degrees here. So, IDC which is leading the voltage by 30 degrees. In other words, the teaser transformer and each half of the main transformer all operate at different power factors. Obviously, the full rating of the transformers is not utilized to its fullest. The teaser transformer operates at only 0.86 of its rated voltage, and the main transformer coils operate at cos 30 degrees power factor, which is equivalent to 0.866 to the main transformers coil working at 86.6 percentage of their kVA rating. Hence, we can conclude that the capacity to rating ratio in a TT connection is only 86.6 percentage of the full load kVA rating. So, here are some of the applications of Scott connection. The electrical furnace installations where it is desired to operate two single phase furnace together and draw a balanced load from a 3-phase supply. Number 2, to supply single phase loads such as electric trains, which are so scheduled to keep the load on the 3-phase system as nearly balanced as possible. Number 3, to link a 3-phase system with the 2-phase system with flow of power in either direction. Now, let us move on to the last and final configuration, open delta or VV connection. So, in connection of 3 single phase transformers, that if one of the transformers is unable to operate, then the supply to the load can be continued with the remaining 2 transformers at the cost of reduced efficiency. This connection is called as VV connection or open delta connection. Here you can see, here there is a open. So, this is not the normal delta connection. So, here one portion of delta is open, here the one portion of delta is open. You can see it here in the next slide. Consider the figure 4.16 in which a 3-phase supply is connected to the primaries. At the secondary side, 3 equal 3-phase voltages will be available on no load. If one of the transformers fails in delta bank, and if it is required to continue the supply even though at reduced capacity until the transformer which is removed from the bank is repaired or a new one is installed, then this type of connection is most suitable. When it is anticipated that in future there could be an increase in load, then it requires closing of open delta. In such cases, open delta connection is preferred. The load that can be carried by VV bank is only 57.7% of it. It can be proved as follows. Here you can see the VV connection. So, this is the normal delta connection. This is the primary side and this is the secondary side. So, here one phase is missing. Here also this phase is missing. So, it can be seen from the figure 4.17a that delta capacity is equal to root 3 VL IL, that is root 3 VL into root 3 I phase, because in a delta connected circuit the line current is equal to root 3 times the phase current, or I can write here in delta line current is equal to root 3 I phase and EL is equal to E phase. So, I can very well replace this IL with the root 3 I phase. So, in delta capacity it is root 3 into root 3 you get 3. So, 3 VL I phase. It can also be noted from the figure 4.17b that the secondary line current IL is equal to the phase current I phase. So, VV capacity is equal to root 3 VLIL, which is equal to, I can replace this with the I phase, dividing the equation 2 by equation 1 we get, thus the 3 phase load that can be carried out without exceeding the ratings of the transformer is 57.5% of the original load. Hence, it is not 66.7% which was expected otherwise. So, consider 3 transformers connected in delta fashion and supplying their rated loads. Now, one transformer is removed, then each of the remaining 2 transformers will be overloaded. The overload on each transformer will be given as, so on the numerator side you have a VV capacity and denominator side it is delta capacity. So, already we have derived this expression, it is root 3 VL IL I phase divided by 3 VL I phase, which is equal to 1 by root 3, which is 55.7 percentage of the full load rating. So, this overload can be carried temporarily if provision is made to reduce the load, otherwise overheating and breakdown of the remaining 2 transformer would take place. Here are the few applications of open delta systems. The open delta system is used in one of the following circumstances. Number 1, as a temporary measure when one transformer of a delta system is damaged and removed for repair and maintenance. Number 2, to provide service in a newly developing area where the full growth of load may require several years. In such cases, a VV system is installed in the initial stage. This reduces the initial cost. Whenever the need arises at a future date to accommodate the growth in the power demand, a third transformer is added for delta operation. The addition of one transformer increases the capacity of the total bank by 73.2 percentage. Now, we will switch on to the parallel operation of 3 phase transformers, and here are the conditions. The transformers are connected in parallel when load on one of the transformer is more than its capacity. The reliability is increased with the parallel operation than to have a single larger unit of transformer. The cost associated with maintaining the spares will also be less when 2 transformers are connected in parallel. The following conditions have to be met with or to be satisfied while connecting 3 phase transformers in parallel. Number 1, the transformers connected in parallel must have same polarity, so that the resultant voltage around the local loop is 0. Number 2, the relative phase displacements on the secondary sides of the 3 phase transformers to be connected in parallel must be 0. The transformers with same phase group can be connected in parallel. As the phase shift between the secondary voltages of a star delta and delta star transformers is 30 degrees, they cannot be connected in parallel, but transformers with plus 30 degrees and minus 30 degree phase shifts can be connected in parallel by reversing the phase sequence of any one of them. Third point is the voltage ratio of the 2 transformers must be same. This prevents no load circulating current when the transformers are acting in parallel. As the leakage impedance is less here, with a small voltage difference, no load circulating current is high, resulting in larger I square R losses. Number 4, the ratio of equivalent leakage reactance to equivalent resistance should preferably be same for all the transformers. If there is a difference in this ratio, the phase angle of the two currents show divergence. One transformer will operate at higher power factor, while the other transformer will operate at lower power factor. Due to this effect, the given load will not be shared proportionately between them. Now, we will switch on to 3-phase transformer vector groups. According to British standard, transformer terminals are brought out in rows with high voltage winding on one side while low voltage winding on the other side. They are lettered from left to right facing the high voltage side. The high voltage terminals are often represented with capital letters, example A, B, C, and the low voltage terminals are represented with small letters small a, B, C. If transformer has tertiary winding, then it is represented in capital letters with enclosed in circles. So, if a phase is like this, I will write it down. So, if a terminal shows letters like this, so this represents tertiary winding. Suppose if this is A, it represents HV windings. The neutral terminals are represented after line terminals. The two ends of each winding are designated by subscript numbers 1 and 2. If there are intermediary tappings, these are numbered in order of their separation from end 1. Example, if HV winding is on phase B, has 3 tappings, then it would be represented as B1, B2, B3, B4, B5, with B1 and B5 forming the phase terminals. If the voltage induced in HV phase B1, B2 is in the direction of B1 and to B2 at any given instant, then the induced EMF in the corresponding LV phase at the same instant will be from small b1 to small b2. The polyphase transformers are given some symbols to show the type of phase connection and the angle of advance turned through in passing from the vector representing the high voltage EMF to that representing the low voltage EMF at the corresponding terminal. The angle of advance can be represented by a clock phase hour figure. The HV side phasor is considered as minute hand, which is always set at 12 o'clock position, and the corresponding LV side phasor is shown with hour hand. Here you can see this. So, this LV phasor is represented by hour hand and the HV phasor is represented by the minute hand. For example, if the connection is written as capital D small y 11, then it represents the high voltage side is delta connected, while the low voltage side is star connected in a given 3-phase transformer. The LV EMF vector in a given phase combination is at 11 o'clock position, that is plus 30 degrees in advance of the 12 o'clock position of the HV EMF position. This is represented by the figure 4.18. Finally, the groups into which all possible 3-phase transformer connections are classified and are given below. Number 1, group 1 is equal to 0 phase displacement, y 0, d 0, dz 0. Similarly, group 2 is 180 degrees phase displacement. Group 3, 30 lag phase displacement. Group 4, 30 lead phase displacement. So, everything, all the groups are integrated and given in the table. On the nameplate of the 3-phase transformer, the vector group is written as yd11, dyn11, etc. The typical representation of the vector group could be yd1 or dy11, etc. So, letter Y represents the star connected high voltage, small y represents star connected low voltage, letter D, capital D represents delta connected high voltage, small d represents delta connected low voltage. The third numerical figure says the angle of phase shift based on the clock convention. The minute hand is used to represent the primary phase to neutral voltage and always shown to occupy the position 1 2. So, here they are clubbed together, everything is given here, all the possible groups, group 1 to group 4 here. The hour hand is represents the secondary phase to neutral voltage and may, depending upon the phase shift, occupy the position other than 12 as shown in the figure 4.19 below. So, I can zoom this on, you can see here. So, this is dy1. So, windings and terminals, then EMF vector diagrams, equivalent clock method representation. Here you can see this is delta star, star delta, again delta star, star delta. Then phasing out test, polarity and phasing out. While connecting a new transformer, special care should be taken to follow the diagram of connections supplied by the manufacturer, taking into account the phase sequence of the supply. In case of 3-phase transformers, if connections are not made in correct phase sequence, the outgoing supply may also be of wrong phase sequence. This would require breaking down of connections and remake of the high voltage cable connections. Whether the phase rotation is clockwise or anti-clockwise, it should be the same for all the transformers that are connected in parallel. However, it is recommended that the standard phase sequences in accordance with the Indian and international practice, namely red, yellow and blue sequence in the anti-clockwise directions, should be adopted. A positive check will help in ensuring correct external connection. The simplest way is to connect two transformers in parallel on primary sides and connecting the secondary terminals of one transformer to its bus bars. After ensuring that both transformers are on the same tap voltage reading between the remaining secondary terminals of the two transformers and the bus bars be taken. If both the readings are 0, the transformers are of same polarity and phase rotation and the connection may now be made permanent. It is also possible for the voltage reading to be double that of the secondary voltage, which when the voltage reading happens to be across unlike phases. It is therefore necessary that care is taken to see the range of the voltmeter is equivalent to the sum of the secondary voltages of the two transformers. Then we will move on to the most important topic, pairing of transformers. Pairing refers to the paralleling of transformers. While pairing of transformers, the following points have to be met or to be considered. Number 1, the vector groups of the transformers must be same. Number 2, transformers from group 1 and group 2 can be paralleled by suitably changing the internal connections of one of the transformers. It is also possible to connect the transformers of vector group 3 and vector group 4 by suitably changing in the external connections. The transformers in either group 1 or 2 cannot be paralleled with either group 3 or group 4. So, before concluding this session on the various types of configurations of a transformer, we will have a quick recap of whatever we have dealt in the class. So, we have analyzed many configurations like star delta, delta delta, delta star, then delta delta. So, VV connection, Scott connection. So, and finally pairing of transformer, that is connecting two transformers on parallel, what are the conditions to be met with. Thank you.